All right, good morning. Welcome back for round two of distance learning, second half of quarter four. Yeah, I hope you had nice long weekends. Yeah, we're kind of right about halfway through our quarter. Makes sense. We're exactly where we would be in terms of content if we were all together at school. Yeah. I think there's only one housekeeping thing before we jump in, which is if you are kind of joining us here for the second half, if for whatever reason the first half was not your deal, this is actually a great time to jump in. We've done 2 units so far. This is our third. So the first was polyatomics, solubility, types of reactions. The second was stoichiometry, all the stoichiometry, all the mole conversions, mole ratios, stoichiometry, limiting reactants. And this third unit that we're about to get into is all about gas. Everything you could, well, maybe not everything, but many things that you could possibly hope to know about gases, what they do, how they behave, how we use them, what's going on with them. Yeah, so you can actually jump into this unit without having conquered, like, you can do this unit and unit 2 at the same time, and that's fine. Yeah, I know there's some folks in that boat, so I wanted to just let you know that you can jump in here and you will be okay. I think that's all. Let's do it. So this first day, usually what I do on the first day of this unit is hand you all balloons, and then ask you questions like what's going on. So it's the kind of day where like you lead, like so here's your balloon, and sometimes these are balloons, sometimes there's these little air pockets if you get shipments of stuff from Amazon, or like packing materials, like sometimes I'll give you packing materials and just hand them out around the room and say like, what do you notice? What is going on? You now have a trap sample of gas. Poke it. What's up with it? Bags of chips are excellent examples. If anyone has a bag of chips in their bag, we can poke the bag of chips. Anything that uses air, and eventually we'll start to like broaden this, right? Because tons of things actually use trapped gas. But just initially, what do you see? What do you observe? Eventually, to what do you measure? Often people observe that when you poke it, it kind of pokes back. That's a thing you could observe about your trap sample of gas. There's a certain amount of poking you can do to your trap sample before it untraps itself. And I usually just let you take this class and run with it, honestly. Because there's so much to know and do and so many places to go. And online, I don't know, it's hard to simulate you all being here with me when you're not. So I think what I'm going to do today is just give you information and then have you watch a video and take some notes on the video. Unsurprisingly, we'll calculate tons of stuff coming soon, but not. I'll show you some conversions today, but we're not gonna get into lots of math yet. That'll be tomorrow. But doop 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 doop. Okay, I'm gonna pretend like you're here with me and do some of this stuff. So you notice that when you poke it, it pokes back. There's a word for that. And if you're following along in the packet, We are on this page, which I think is right after your chocolate chips and chocolate chip cookies. Kinetic molecular theory, which we're going to shorten to KMT every now and then. We should probably break this down and figure out what kinetic molecular theory is. This is page 61 if you are in the packet. This page does not have a printed back, which is kind of an issue. What the back should say is this. Oh gosh. Okay, I'll give you the name of the back later because I want you to come up with that too. Okay, so the first thing though, well, second thing, we're going to start with this table. Gas variables. If you do not have this page, you might want to copy this onto your paper. I'll just copy it right here. Things we're looking at: variable, symbol, description, metric unit, and a non-metric unit. And we're going to use the metric units and not use the non-metric units for the most part. And I do this next to our little balloon. You poked your balloon, you saw it poke back. That is called pressure. You poking your balloon is pressure, your balloon poking back is pressure. You can measure how pokey-backy your balloon is. Some balloons have less pressure, some balloons have more pressure. When you poke them, they respond. How much force? Well, let's do your symbol. Symbol is P. Don't overthink that one. So if you're measuring pressure, you're gonna say P equals something. P is how pokey-backy it is. How much force does your gas generate over a given area? Let's write that down and we'll figure it out. So how much force does your gas generate over a certain area? So how much does it poke you back if you give it like a doop, little poke versus like a bigger kind of poke? The size, the area that you're poking with is the area in this equation. So like a little tiny area will give you some amount of pushback. A bigger area is going to give you a bigger amount of pushback. We usually take your trap samples of gas and we will like squish them between your hands and we say, you're a big strong human and you're poking gas. You're poking these little particles of gas and you can't even make them disappear. You can't squish them. You can put enough pressure that you pop your container. That's something that can happen. But so the amount of force that it generates against you divided by the amount of area that you're generating, like the amount of area that it's pushing back on, that's its pressure. You might recognize pressure from your tires. Your tires are measured in pressure. How much pressure is in your tires? How much force is generated by your tires to keep your car not on the ground? If you have a flat tire, right, like it loses its pressure, it has a hole in it, then its force decreases. But if your tires have the right amount of pressure, it's that force generated from the air that's keeping your entire car off the ground. So air can have a lot of pressure. You can really pressurize a gas. And then units. Off we go. Okay, so non-metric units are things you probably know a little bit better. When you're filling your tires, you might be doing this in PSI, which is pounds per square inch. I'm just going to zoom over here a little bit. PSI is pounds per square inch. Other units that you may know of, This is the word I didn't give you on the back, but most of our gas on planet Earth is found in the atmosphere. That is another unit for pressure. You can measure how much force the atmosphere generates on you over a certain area. That's the pressure of the atmosphere. Just to point this out, this sometimes looks like atom, which is legit, but it's not. It is atmosphere. So ATM gives you cash sometimes, or is the abbreviation for the pressure of the atmosphere. The metric unit that we will use, it's possible that you've never seen this before, which is fine. We're going to use the unit of kilopascals. So we've got a little k because it's a kilo. I'll just write this out. That is a kilopascal. Pascal was a human who did work with pressure. Just realized that pressure and Pascal start with the same letter. How has it been this long night? Whatever. So kPAs are your desired unit of pressure. When we get to the bottom here, we'll do some conversions so that you know how to go between these things. But for now, let's just give you that. Usually when we're in class, we'll kind of fill out this table depending on where your thoughts and conversation go. Because at some point along here, you're still looking at your balloon, your packing peanut, your whatever, bubble, packing bubble. And what else do you notice about it? You might notice that it takes up space. There's space inside of that balloon. I said, yes, definitely. What is a fancy math science term that you know for taking up space? And someone will say volume. Symbol for volume, unsurprisingly, is V. Probably matches math class also. Volume is description, how much space it takes up. How much space. And you might recall from geometry that there are all sorts of exciting equations that you use to find volume of different shaped objects. Here, you don't have to worry about that because our objects are going to have really weird shapes. And so, we're just not even going to worry about that. We'll say that volume is how much space something takes up, and we will calculate it, don't worry. But we're going to get there a completely different way than math class. They're both valid, but ours would need calculus, so we're not going to do that. The units for volume and non-metric units for volume. Non-metric units include things like gallons, cups, right? Things that measure how much space something takes up. Metric units, similar to gallons, but the metric equivalent is liters. We will be using liters to measure volume. And you do not have to solve for the volume of a sphere or anything like that because you put pressure on your balloon and it is no longer a sphere and it didn't start as a sphere anyways. Cool. There are 5 of these. We're going to keep on keeping on. And by 5, I really mean 4, but I've given you 5 spots in that table, which is a little bit confusing but intentional. Other things you can measure about your gas. Sometimes this unit falls in January, and we will take our trap samples of gas out the back door and measure their change in temperature. Unit symbol for temperature is T. Description, description of temperature has to do with energy. Temperature is energy, temperature is motion. Temp is energy, and really it's a measurement of motion. How much are the particles moving? That's the description of what temperature is. It kind of makes sense. You go for a run, you feel hot, you know, lay down and get really calm. You might feel cold. Same thing. Temperature is like heat is the energy of motion. Units. Here in the US, we are most familiar with Fahrenheit. We will not be using Fahrenheit. Don't even worry about that. It's something about 5/9 plus 32 or whatever. We're not even going to go there. You may also have, there's a common, okay, so there's a metric unit that we're going to not use. This one. Celsius and Fahrenheit are both units we're not going to use. The unit that we are going to use, again, may never have heard of this before, similar to kilopascals, kPa. We're going to be using the unit of Kelvin. What is a Kelvin? Why do we care about Kelvin? So if temperature is a measurement of energy in motion, what Kelvin does for us is it lets us measure how much energy in motion as a net positive. So the entire Kelvin scale only exists as positive numbers, which lets us compare how much motion without going negative. So you live in Minnesota. Even if we're measuring in Celsius, we go negative all the time, but it doesn't mean that the particles have stopped moving. You know, like you can be outside in negative temperature and walk, right? You can still move even if you're in a negative Celsius measurement, if that makes sense. Kelvin, on the other hand, only describes motion, and it essentially sees all motion as a positive number. There's a fancy term as Kelvin approaches 0, which usually I'll pitch that to you, and somebody will be like, oh, absolute 0. Absolute 0 is 0 Kelvin. 0 Kelvin is 0 that. It is this theoretical, conceptual thing that we've never achieved, and some people argue a lot that we'll never achieve, which is the absence of motion, of particle motion. So for decades we thought this was negative 273 Celsius, was 0 Kelvin. Maybe 5 years ago somebody published an article, it's actually closer to negative 273.15. Anyways, so it's real cold. It's real cold. Way beyond where liquid nitrogen turns solid. Down by where helium turns liquid at 4 Kelvin. Anyways, Kelvin measures all motion as a positive thing. We've never achieved 0 Kelvin, which is absolute 0, which is 0 motion. But we will use Kelvin because we'll think of energy and motion as being like positive amounts, which is only possible in the Kelvin scale. Alright, that was your intro to Kelvin. The last variable, so thing that can change, that we're going to be looking at is, you take this balloon, before you tie off your balloon here at the bottom, you can inflate your balloon, or you could put a hole in the side and deflate your balloon. You can measure the amount of stuff. Whoa, what was our science word for amount of stuff? Yeah, you can measure the amount of stuff inside the balloon. So amount of particles. And there was a fancy word for amount of particles. We will call that moles. The symbol is N. N is the number of particles. Oh, I should have written number. Yeah, number of particles is N. Amount of particles, same deal. Don't overthink this one. Description, number, amount of particles. And there's your unit right there. We've got the unit of moles. I'm not sure if I said this last unit. I probably should have. The abbreviation for mole lops off the E. So these are the same thing. This is the abbreviation. This is the full spelled out word. M is not an option. M means mass or meters. Do not use a single M. But MOL is just fine. That just means mole. Non-metric units, I mean, we could count the actual number of particles with Avogadro's number, so it's 1022 times 10 to the 23rd. It's too many. Don't deal with it. You do, however, you know how to convert from grams to moles. You know how to convert from liters to moles. You can, that was your volume conversion from last unit. You can totally, at a gas, at standard pressure and temperature, things are going to get a little weird here. But, so you can convert other things to moles. Yeah, but the number of particles we'll measure as moles. Okay, good. So those are your 4 variables. The last thing on that list is the ideal gas law constant, which is not a variable, it is a constant. And for right now, let's give you this and then actually leave it here for now. The elusive R. The elusive R is a constant. It is our gas law. I should say our ideal gas law. We'll get there in maybe a week. Ideal gas law constant. So that is a number. It is a constant. It will not change. And let's figure out its units later, because that's going to get kind of messy. Preview of the future. The unit for the ideal gas law constant includes all of the other units, which is what is most likely to mess you up about it. So the unit of R includes all 4 of these units. So we're gonna get some practice using them, figure out what they mean and what to do with them, and then like a week from now, we'll figure out what is going on with R. All right, nice. So that's that. I think I'm going to do a separate video to get you the principles of kinetic molecular theory. If you're on this page, that's the other half of this page. Cool. We'll be right back.